Good morning, everybody. So this is week 3 of the information retrieval lecture. I will start, as every week, with a recap of what we did the week before. And I'm going to start with some clicker questions. So this is small warm-up. So what do you call this? Anybody remembers? Let me try something else. Who knows? Oh, yes. Tell me. An inverted index. Yes. And I'm going to have to add one word on top, standard inverted index, for reasons that will become clear this and next week. So this is a standard inverted index. So I'm not telling you anything, but here are a few clicker questions that are coming. So first, if you look at this inverted index, I'm giving to you 6 documents. And I would like to tell me which ones, multiple answers possible, which ones of these 6 documents could have. I'm going to have a set of questions like this, but they are all using the same inverted index. So this should make things easier. We have one answer in. Two. Yes? The way that it works is we have a collection of documents, and we are indexing this collection of documents in order to make queries faster compared to a grep, for example. So the indexed collection is the collection that is being indexed by this index, if it makes sense, right? Like the Sherlock Holmes corpus or the Shakespeare corpus, except that in this case, I'm making up words that do not exist just to be a bit formal. So now the number of incoming votes should accelerate. It's reassuring that it looks more like a Gaussian than a Poisson distribution. Okay, 17. So can you raise your hand if you need some more time? Yes, a few. I'm giving a bit more time. Just to check you understand, or how many of you understand, who of you out of this index would be capable of reconstructing the entire document collection? Who of you knows that he would not be capable of reconstructing it? And who thinks it's a good thing? Well, it's normal. Yeah, exactly. So we basically lose information when constructing the index. We lose 2 things. What do we lose? We lose, yes?
Information on ordering.
On ordering, and the other one we lose? Yes? The number of occurrences. So we lose information. So it's normal that you cannot reconstruct the collection, and this is why it's formulated as could have belonged, but you cannot know for sure. Okay, so let's look at what you said. Yes, so the top 2 are the right ones. So let me close. So let's go through them. So you can see that the 2 document tools, they have exactly the same terms and the same, well, we don't care about the ordering and the occurrences, so they would be indexed in the same way. So yes, they are potential candidates. Document A and document E, this is just topsy-turvy. It's not this way around, right? So the terms are A, B, C, D, F, G, D, E, F, G in yellow, and the documents ID are in blue. So this is here, it got it wrong because it's inverted. We use the terms to designate the documents and the document IDs as terms. So this is why this is wrong. The first and third answers are wrong. The third, document 3, why is it wrong? Yes? Yes, exactly. It should also have E and G, and it doesn't have them, so it cannot be. And the last one, it's the opposite, right? It contains too much. It contains G, but it is not, document 4 is not in the postings list of G. Okay, so now let's do queries, and let's try to make it as fast as possible by increasing order of complexity. So I still have the same postings, so if I say A and B, what do I return here? A and B. Which documents satisfy the query A and B? This should be quick. This is really easy. $16. We had a bit more than, I think, 23 last time. 2 more. 21, 22, and 23. There you go. So let's look. And this is 3.8. So what you are doing to compute the results of the query A and B is the documents that contain the term A and that contain the term B. So this is the intersection of the two lists corresponding to A and B. So 1, 2, 3, 5, 7, 8, and 3, 4, 7, 8, 9, 3 and 8 are the documents they have in common, right? So the correct answer is 3 and 8. And the first answer would have been the union, but this is an AND query, so it's the intersection, not the union. The first answer would have been A or B, if I'm correct. So all of the documents. Okay, so let's get to the next one, which is an OR query, C or D. Also, as quick as possible. This should really be easy. You know, there's several steps in the learning process. There is the step of understanding what problem we are solving. There's the step of solving it correctly, which grep does. There is the step of solving it efficiently, which is what the inverted list does. And then there is the step that it is so natural to you that you don't even have to think so much. This is like learning a language. When you learn a language, you first have to think to make sentences, but at some point it just comes like this. And this should really be something that comes naturally. And when you implement it, it will be even clearer. Okay, 24. So yes, the correct answer, you were right, was everything but document 6. Why not the second one? Because you can see that document 6 does not contain C, because it's not in the postings list. And document 6 also does not contain D, so it cannot be in the results of C or D. Okay, next one. So this one with an AND not, and you'll have exercises on this. So D and not E, what does it return? Wow, you're really getting quicker. That is very nice. So don't worry, as I said, for the exam, we'll try to have no time pressure. I'm just putting time pressure right now to push you a bit. Very good. 1589, because you can see that if you look at it's D and not E, you have 3 that is in E. So this is why it's excluded, because we're looking for documents that do not contain E. So this is why 3 is taken out and 1, 5, 8, 9 are not. And now, a bigger one, and here you'll have to think a bit more on how do you do that efficiently. So what documents does the query A or B? I put the parentheses because OR normally has a lower precedence. So A or B and E and F or not G. Be clever. You should not necessarily compute it in exactly that order, because you know that AND and OR are associative and commutative. By the way, what do we call this form here? This form of a Boolean formula? Either the abbreviation of it or the name of it. Yes? CNF, yes. And CNF is for? Conjunctive normal form, exactly. So we already have 6 answers. Asking these kind of questions is also stressful for me because I'm always afraid of myself making a mistake in there, but I hope not. "18 answers. I'm waiting for 6 more, 4 more, 20, come on, 22, 23, 1 more. And do we have a 24? Okay, yes, we do have. So the solution is 2 and 4. And again, you are right. Who can tell me how clever you were to solve it? What did you do? You have a couple of ends, yes?
Well, we know that A or B does every possible verb document.
Yeah, you are correct. Yeah.
Then when we end this with E, we just get E.
Yes?
And then we just have to end E with the F or not G, and F or not G is like zero.
Yes, so basically 2 and 4 are in F and they are not in G, that's why. What would you have done if you did not know that A or B was the entire document collection?
Ordering by size of the...
Yes, so basically you would have seen that here we have disjunctive queries. So if we have a single term, so basically we have E here that is both alone, not in a disjunction, that would make it even bigger, and it's relatively small. So you should have normally had the insight of saying I'm starting with E and then I'm removing documents in the 4 documents that the posting list contains. Okay, to whom is this all clear? Very good. So now let's continue. So we had this first approach to information retrieval, where we have a model of the world. And the model of the world is we have an input, which is a collection of documents, a set of documents, and we have a query, and we want to output a subset of the original documents. So this is the overall problem. We have a simple Boolean language. I'm even giving you the EBNF here, and the TA team has even implemented a parser for this. There is nothing much to it. You know what a context-free grammar is and how this works. And what we did is we abstracted away. We abstracted away because originally we have a list of words, the order is important, and we have the duplicates, but we simplified this, and instead we're saying we have a set of words. Set means we throw away the order and we throw away the number of occurrences. Okay? A bag of words would have preserved the number of occurrences, right? So then we simplified further the documents as vectors of Booleans, meaning that here we have terms, we have the entire list of terms that appear in the collection, and we have this vector. Who is attending the machine learning lecture, Introduction to Machine Learning? Who remembers seeing this in the first week? Yes, you did, right? This is exactly the same kind of models that you have on the machine learning side when you have the terms as features. Okay? And then what we did is another way of looking at it is this is a single document here that we abstract away, and then we took the whole collection of documents and we represented it as a bipartite graph between terms and documents, okay? And in here we do also forget, it is a set of terms in this case, okay? And then what we did is that we looked at representations of this. One representation is called the adjacency matrix. It's just one of the ways of representing a graph. More precisely, this is the adjacency matrix of a bipartite graph. Because if you actually look at the adjacency matrix of the graph, if you don't know that it's bipartite, you're going to have a lot of zeros everywhere, and this is actually just one quadrant of the overall matrix. So when we have a bipartite graph, we just simplify the adjacency matrix by having the documents on the columns and the terms on the rows. Okay? So the adjacency matrix of the bipartite graph, and even better, and this is our index, the postings list. Okay? We will come back to this when we see the vector spaces, which is an alternate way of modeling the information. But right now we have this inverted index with the postings in there. So this is what we've been doing last week. And I know that for some of you it was very easy, maybe almost trivial, because how hard can it be to just list for each term the documents in which it appears, and then it's obvious that you intersect if you have an and, you union if you have an or. But you should also, when you look at this, look at the big picture of what is it that we are doing here. We are abstracting away from the world, exactly in the same way that for relational databases, we abstract away from the world saying everything is a table. We also have this kind of indices using different kinds of technologies, but the ideas are exactly the same. And what I would like to tell you here is do not underestimate the power of simple things, because simple things help you do something correct, and you know that you fully understand something when you are able to explain it in very simple terms. And I like to tell the story of French mathematicians who you may know. Who knows Évariste Galois? Who heard of him? Some of you, not everybody. So he's actually the person who came, who invented the whole concept of abstracting away to groups and rings and fields and so on and so on. And when he started doing that, what he was basically doing was taking something that you teach in primary school, meaning how to add numbers, addition, multiplication, and so on. And then he abstracted this away, saying we can just give symbols like to represent the members of a set, like ABC and so on and so on. And then we can define symbols like plus and multiply, like A plus B, A dot B, and so on and so on. And then we can come up with abstractions of what these operators can have, like commutativity, associativity, and so on and so on. And the first reactions when he was doing that was that the most established mathematicians of the time were laughing at him, because they were telling him, you're doing primary school stuff. What you are doing is totally trivial. And as it turned out, this extremely simple abstraction of the concept of a set and looking at properties and talking about groups and rings, when you take it to the next level using these constructions, this is how you start building very rigorously the set of complex numbers and demonstrate very powerful theorems. Like, for example, what you can draw with just a rule and a compass, and so on and so on. So it is extremely simple. It was underestimated at the time. But the power of abstraction and simplifying things as much as you can, in a way, this is what researchers are doing. When you start working on something, at the end, you want to be able, once you've done all the work, to explain it in very simple terms, right? So this is exactly what we've been doing last week, and this is something very general in the fields of data science and databases. You want a data model, a very clean data model, a very clean language. You want to be very clear what your language manipulates. By the way, what does our language manipulate? The Boolean language. What do we return every time and work on? Okay, let me tell you. It's just postings list. Every time you have a term, or A and B, or A or B, or A or not B, or any query, everything can be mapped to a list of postings. right? This is the data model of the very small and trivial query language that we have designed, but you need to understand it at that level of abstraction and not just thinking, oh, it's simple, it's just a bunch of rows and lists and we just intersect lists. This is really on the abstract level that you need to understand this, because we are going to extend this, we are going to make it more robust. So to be very precise on the vocabulary, a document is one of these things here. It's a column here in the adjacency matrix, and it is the set here, the equivalence class of all the postings that have the same document ID. So this is the same document here. So this is a document. This is a term. I will tell you about type later. This is a term. It's the other side of the bipartite graph, document term. It is a row in the adjacency matrix, and it is one posting list in there. A type, we will look at it today. It's an equivalence class of terms when we try to group them meaningfully. And finally, something that's called a token or a posting. I think the book calls it a token, but in terms of data structure, you would call it a posting. It's a pair of term documents. It's an occurrence of a term in a document. In programming, you have the word use when you say, for example, document use or term use would be the name you would call it programmatically. So this is a pair of term documents. It is one cell in the adjacency matrix, and it is one single posting here. Do not be confused. Here, we only have the document ID that we store here. But implicitly, there is also the term here that it's associated with. So here, this is really a pair of the term in the documents, right? The fact that we leave out the term here is only a space optimization because we already store it there, right? But this is really a token. It's called a token. So document, term, token, an occurrence of a term in a document. Okay, very good. So you probably think it's very easy, and you are going today to implement this in Python. But what I would like to show you today is that this is actually more complex than it really seems. Because in the exercises, we are basically going to directly give you the set of documents. We are going to tell you what the documents are. We are already going to give you the tokenizer in order to say what the terms are. So we are going to give you a lot that is already prepared, so that you can really focus on just implementing the inverted index. This is for you to stay focused. However, it's actually much more complicated than that in practice, because in the real world, it's just more complex than just white magic to turn this into this. So in the real world, we need to tokenize the documents. We need to determine what the documents are, and then to tokenize and find the terms in there. This is something we are going to talk about today. We need to do some linguistic pre-processing, because sometimes you would like to acknowledge, for example, that cat and cats, you're looking for the same thing, right? So this is also something that needs to be done. And then only you build the index. And last week, or this week in the exercise session, we are only doing this. This is already done. This was done by the TAs, basically. So today we are going to look a little bit into these things, like the real-world problems that we have. So first, the documents. What we start with when we want to index something is to determine the documents that we are indexing. If you are a library, it's actually extremely simple. You can consider that the document is a book, or it's a DVD, or it's a tape, or whatever. It's what you can hold in your hand, basically. I don't think that, I don't know many librarians that would start tearing the books apart and saying, I'm making 2 documents out of that book and so on, right? But if you are looking at digital data, it is not as simple as it seems. If you have a sentence like this, first you need to look at the storage, because it's digital. It's a digital version of the document, so it's not just a printed document. So what it needs is that you need to look at how this is mapped to actually individual characters. So the simplest way you can look at a document, if it's text, is that it is a sequence of characters, okay? So it looks pretty simple if you only have this kind of characters, but as soon as you have more, you will see that it's actually kind of a big mess, even in the industry, with the way that this is done. Just to check your knowledge, this is something I'm assuming you know, but one of these 4 here is not an encoding. Which one? Oh, wow. Wow, you fell into the trap. I actually, on purpose, did this macOS Roman in order to try to trick you, but wow, okay. So yes, sorry, macOS Roman is an encoding. It's an alternative to the one used on Windows or the Latin one encoding. Okay, the right answer is Unicode. What is Unicode? It's not an encoding, it is a character set. What Unicode does is that it gives you a number for each character. It's just mapping a character to a number, like a catalog of all the characters. But Unicode does not tell you how to encode things. And Unicode has many ways of encoding things. There is UTF-8, UTF-16, UTF-32, so there's plenty of different encodings that use the Unicode character set, right? But Unicode is not an encoding. It is only a catalog of the characters. It gets updated every year with new emojis, which seems to be now what the focus is about nowadays. So this is a character set. A character set is just the set of the characters that you support. And this is an abstraction of the pixels, because if you have a book, these would be pixels. So when we store in the first computers, it's trivial to us today, but at the time, this was needed in order to actually work on the right level of abstraction. So the encoding is only the second step. So first you have the character set, that you have the sequence of characters, and only then do you actually map that to zeros and ones. The encoding maps the characters, the numbers in the character sets to the zeros and ones. So here you have P, here you have O, here you have S, here you have S. This is here ASCII, right? We are using it's one of the oldest encodings that there ever was, with 128 characters. So this is the ASCII table, actually, as it was, and you can see that every number here is mapped. So here we have the hexadecimal version, so 5 here and 0, and you get 50 in hex, right? So this is pretty simple. We have both the character set here, it gives you the 128 characters, plus the encoding, which is just the binary representation of the number. So this one is pretty simple. It was one of the earliest. UTF-8, which is one of the possible encodings associated with Unicode, is slightly more complicated. The idea of UTF-8 is to try to be efficient, because very often in text you are going to have ASCII characters. You are going to have just letters, Latin letters. So if this is the case, then it shouldn't take too much space. So even though technically the Unicode character set supports, I think, 32 bits, like 4 billion of characters, in practice, you don't want to use 32 bits every time. So what you do is, if it's less than 7 bits, meaning that it's in the ASCII character set, then you have here these 7 bits, and you have the 0. And if you see something starting with a 0, you know that it is less than 7 bits. And then you have your characters here, okay? If it's more than that, right? If it's, for example, the letter pi, then it has a bit more bits. It has 10 bits. Less than 11, which is the next bound, then you start encoding it. You say 110. So if you see 110, then you know that it's between between 8 and 11 bits. 110, so here you have 5 of them, and here you have 6 of them. And you see 5 plus 6 gives you 11, so everything is consistent. So 110 is like some meta information that tells you, beware, these are 2 blocks here, because we have more than 7 bits. And 10 is just the way of telling you this is the next block, okay? Who understands this? Who already knew this? Some of you, but not all, okay? And then finally, if you have even more, like this, the euro symbol was invented later, less than 16 bits, and then you have 1110, and then you have 2 more blocks instead of just 1. So you see that we are compressing stuff here. We are compressing because for the simplest characters, we only take 8 bits. For the more involved one, we take a bit more. So this is what UTF-8 is doing. There's plenty more. There's UTF-16, which does the same thing, but it takes this as the default rather than this. So it has 16-bit blocks. And finally, UTF-32, which is the simplest ever, as it simply encodes every character as the binary representation, always in a 32-bit blocks. But in practice, UTF-8 is really what is encouraged. Everybody's using UTF-8 nowadays. Okay. So the first challenge, because here I'm telling you this is the encoding, UTF-8 or ASCII and so on. In practice, you may have documents that you don't even know the encoding of. So it means that you need to actually find techniques to discover what the document was encoded in, because if you don't have that, you cannot even read it or start indexing it. So that's the first challenge. And the way you do these kind of things is actually something that goes more on the machine learning side. So not just the encoding, but other things like what language is the document in and so on. You use machine learning techniques, and this is why we are not going to cover them. But you should know that there is an interaction between information retrieval and machine learning, because in machine learning, you can have a training set with documents annotated with an encoding, and then you build a model and you train it, and then you get as an output for the documents, for your real documents, you get the encodings or the languages and so on. So this is where machine learning can be useful to information retrieval. But as I said, this is covered in a different lecture. Something else is that there may be even software-specific encoding. Maybe you don't even have a text document with ASCII, UTF-8, and so on. You may have a PDF or a Word document. So a PDF would be, so in the worst case, even a binary document. Word is just a zip file containing some XML stuff, so you can still read it as semi-structured data, even though XML is already a special topic in its own. And in that case, you may have some encodings. Who is familiar with XML? Some of you. So you have encodings like this in XML. So you see that this has nothing to do with ASCII or whatever. It's just a way of encoding the ampersand, of encoding smaller than, and so on. These are all things that you need to deal with. When you start indexing a collection in the real world, you need to deal with that. You need to make sense of all these documents. And I can tell you, if you have 1 billion documents, some of them are PDF, some of them are Word, some of them are like a huge collection, this is really not trivial at all to do. So I already told you that. Another thing that you want to classify is the language, because in some cases you do want to know the language of the document. This week we are not even looking at the language. I mean, we know it's English in the exercise session, I mean, but we just tokenize with white spaces, so who cares that it was English? We could have done it in German, in French, in Italian, in any other language. But we will see that the language, having the information about the language of the document, is something that matters. And the document type as well, because of the software-specific encodings. Okay? So this is the first challenge. The second challenge is something I already told you, is how do you delimit documents? In a library, it's easy. A book is a document. That is easy. The problem is that in some cases, you may have archives. For example, if you have emails in an archive file, you may not want to index to make it a single document. You may want to split it, to open that archive and split it into all the documents. This is exactly what happened with the Shakespeare corpus that the TAs prepared. The original documents were not like the ones that you are going to see. The original documents were much bigger files that we had to split in that way, right? This is also some preparation that you need to do when you prepare an information retrieval index, right? And it's also true the other way around. You may have plenty of documents that you want to group into a single document. That's the case with a LaTeX document. Who already wrote a LaTeX document? Who already used several LaTeX files for a single document? Some of you as well. And in that case, when you index, you still want to consider all the files together a single document. So why, at first sight, it may seem obvious, these are real problems that you deal with in reality. You need to make these decisions on the granularity of the collection of the documents. This is much bigger than just information retrieval. This is true in databases as well, in general. When you store your data, you need to decide how big the chunks of data must be. Okay? So this is the first part of today, where, remember this overview that I gave you, like collect the documents, tokenize, pre-process, linguistic post-processing, post-processing, not pre-processing, and then the index. This is the first part. This is processing the documents, finding out what encoding they are in order to read them, what language they are written in, and so on and so on. And here machine learning is very useful. And then determining the granularity of the document, meaning do we split a document into several or do we group documents together? Okay? Once we have that, the output of this is that we have basically documents that have document IDs because you decided how to attribute the IDs based on how you group the documents. And you figured out the language they have and the encoding they have. So you basically have text at that point that you are ready to index. Okay? So at that point, you can start going to the next step. Going to the next step again, here, if I give you this example, it seems very simple. How do we build an inverted index on this? We actually did it very naively last time, is that we took the words, but we did a few things that I very quickly discarded last week, but it is not innocent. We threw away the punctuation. This is something we did, because we could have said, okay, if we really tokenize here the document with white spaces, then we would have had here our comma as a term, which would be different from this term here, right? And this is undesirable, because if you search, you want this to be found when you say our, right? So this comma here, we want to get rid of. So we can just throw away the punctuation. This is one way of doing that. The problem is this. It doesn't always work, because if you just say I'm throwing away the punctuation and only keeping the letters, then welcome to all these corner cases. You have emails, right? You may want to treat emails in a special way with the @ dot and so on, because you may search on an email, but you also may want to search within an email. So this is tricky. You need to make a decision on that. Then what do you do with this? What do you do with this is specific to English when you contract things, like isn't instead of is not. Do you want to expand it back to is not? Do you want to make it a term, isn't? And so on, right? So this is another example of a family name that may have here an apostrophe in the middle. Do you make it two terms or do you make it one term? Here, this is something also, the dash in English. The dash in English is very useful to group words together to make the sentence clear. The learn it all by heart methodology. Dashes are very complex in English because technically there is no absolute rule on how to use them. I could also have written this without any dash. The basic rule about dashes is just that you put them where it helps make the sentence clearer to read. But the problem is that in that case, it's pretty obvious that you may want to throw away the dashes and index the term all by one by one. But what if you have some usage of the dash, some uses of the dash where you do want to keep this as a single term? This is another example. You know what happened to dashes? When people use a dash between two words in English, usually a few decades later, they start throwing away the dash and pasting the two words. And this is exactly what happened with a lot of words like doormat, keyboard, and so on and so on. So now we have a tendency to write this, for example, as a single word. So of course it makes the problem kind of go away. But when we will look into German, you will actually see it doesn't completely go away. And here, for example, Canton Baselstadt, this could be seen as a single term. It's the name of a state, right? So there's all these things here telling you this is not so trivial. You could say, I'm just tokenizing by white space. I throw away the punctuation. This is not so trivial. You need to look at these things. There is no universal answer. You really need to think about what kinds of documents you are indexing, what language are you indexing. It's a very good idea to look at Google or Bing if you want to see how it's done. They put a lot of efforts into getting these things done in a way that people expect. But again, there is no universal answer. So I'm not going to tell you you should do it like this or like that, but you have to know that this is an issue, and we need to take care of that. Just other examples of dash here. You want to keep the dash because Hewlett-Packard is a company. So you don't want to index Hewlett and then Packard. You really want to index them together. But how do you distinguish with the other one, right? Where you, like state of the art is the same co-education. This one is the kind of dash that can disappear after a while because you just paste the words together. Here again, it's another example. Here there's no dashes, but you still want to treat database, for example, as a single term. Here it's a city, but there's a white space in the middle. Maybe you don't want to throw it away. Here, again, this is tricky, this one. It all comes from the same people that wrote the book, by the way. You say Los Angeles-based company. So you have a dash that says it's based in Los Angeles, but in Los Angeles, you don't put a dash. This is tricky, right? Because you may think we throw away the white space, and then you have Los, and then Angeles-based doesn't make any sense. Here, it's again the same thing with flights, and flights also matter. I mean, people search for flights under Google. So San Francisco, Los Angeles, you have a dash here, so you don't want to tokenize here, and so on, right? Here is another example. If you tokenize like New York versus York, New Orleans versus Orleans, right? Numbers are also something that you would think we could throw them away. If you test under Google, you can actually search for numbers. Wikipedia as well, I think they even have pages on each number. So this is something you may want to index. Here, maybe treat it as a date. Here as a phone number, and so on and so on. So this is also things you need to keep in mind. These are all corner cases, basically. I just want to say this is something you need to think about. Then you have all kinds of languages. This is the start of the Wikipedia page on China in Chinese. And you can see that, so I don't know a lot about Chinese, so I don't want to tell you anything that would be incorrect. Does anybody speak Chinese here? No? So the trick is, as at least is explained in the book, is that names, white spaces are handled in a different way. And you have less white spaces, but you still want to tokenize here. And the tokenizing is not trivial at all, because sometimes you have ambiguities. Sometimes you will have here one symbol that means something, and another symbol that means something else, but the two symbols taken together mean yet something different. And then it makes a difference how you tokenize it. Do you make it 2 tokens, 1 token? It makes a difference in the meaning that you are indexing, right? So when you index Chinese texts, you need to have that in mind as well. But then, of course, it's probably a good idea to learn Chinese to be sure that of what you are doing when you do this. There is another example in German. This is one of the longest words I know. Donau, dann Schifffahrt, Elektrizitäten, Hauptbetriebswerk, Baubeamtengesellschaft. It's not even so easy to pronounce in a single chunk. You'd probably do, well, this one maybe you want to index just for the fun of it, but if you actually think about it, you may want to come up with a way of tokenizing Donau, Dampf, Schifffahrt, with even taking into account the change with the triple F versus 2F and so on, which is yet something else. Then Elektrizität, Haupt, Betrieb, Werk, Bau, Unterbeamten, Gesellschaft. So you may want to cut it in that way. And this here will need some linguistic knowledge, maybe some machine learning as well. You may want to throw some machine learning in order to teach that to a machine, how to split the words. I'm sure that some smart people can even come up with general algorithms to approximate splitting the words. But basically in German, you need to deal with the fact that you're pasting words together that do not have dash. You even have to consider who knows what the Depenleerzeichen is? You probably know it from the FIS, right? Because the Verein der Informatik Studierenden has actually a Depenleerzeichen in the middle. I remember it was discussed in one of the general assemblies whether it would be fixed or not. And in practice, people make this mistake of adding spaces in German as well, right? So you need to have that in mind when you index a corpus. And you have other languages. This is even better than German. It's Negyak Tugyu Gumayag Petalu, which is Siberian Yupik. Does anybody speak Siberian Yupik here? It's actually very hard to learn. I tried to Google for it and find if there was a tutorial somewhere. I found some research papers on some people that traveled to the north and listened to the people. It's actually very obvious to understand. Basically, neg means to eat. Yaktug means go to. Yug means want. Uma is the past. When you want to conjugate something, is the past, very obvious. Then you have yag, which expresses frustration. And then you have PET, which means inferential evidential. Turns out that. This is what you actually mean. When you add PET to a sentence, it actually means it turns out that. And ALU is that you conjugate it to the third person, so you're talking about somebody else. And LU means also. So when you know all of this and you are capable of tokenizing it the right way, it's quite obvious that it means also it turns out he or she wanted to go eat it, but something. This is the frustration part. So you can see that in these languages, when you have a whole sentence attached like that, then you need to come up with yet other techniques in order to paste it all together. I think in Turkish also you have very interesting grammatical features of the way that you paste words together, like iyiyim, I am good, where you paste the whole expression together. It's very interesting to look at languages. I encourage you to do that. I think there's probably an NLP class, natural language processing class, where this is covered. So anyway, what I'm telling you is languages matter because it makes a difference how you actually do the indexing. Oh, I was so carried away by what I'm explaining that I didn't see the time. We should take a break, and I'll see you, so since it's 10:03, I'll see you at 11:03 for a 10-minute break. Start again. So I showed you in many different languages that tokenizing and finding out what tokens to use is absolutely not easy. You even have some things in Swiss German that are very interesting, like, I don't know, sometimes it's different than German, you even invert. For example, es ist nicht logisch, etwas können zu machen. Etwas machen zu können, you invert it compared to German, and the Zmache, if you write it, I think that it's more common to write Swiss German in the younger generations when you text and so on. Zmache needs to be tokenized as zu and mache. So these are all the kinds of issues that you need to deal with. And I think that, I'm not sure if actually search engines, I think with Google you can totally find Swiss German or Zurich German and so on and so on. So basically in any language, you need to think about this, you need to come up with a solution, and I'm sorry I cannot give you the universal solution, but just be aware of it. Okay, so if we want to tokenize, let's say we have taken away the punctuation and so on, and we have meaningfully determined what tokens to use. To say it again, this is something I already told you earlier. A token is really just one occurrence of a term in a document. This is called a token. Right? And I told you type, this word type, which is slightly different. A type is an equivalence class of tokens. For example, this and this is the same token, right? So it can be called a term. You can call our a term. But we will see later that when we start grouping similar terms like our and ours into the same class, we will call that a type. So the terms will be our and ours, but the type would be our, the class of terms. So there's three things in there: token, term, and type. So you need to distinguish between these three things and know what they are. Okay? So who understands the difference between token, term, and type? Who doesn't? Okay. So if you have any doubts, ask again, or I can come back on that next slide. So a type is an equivalence class. This is another example. So here it's easy because it's exactly the same term. So here it's an equivalence class with just one term. But we will see that we want to do better than that. Somebody last time told me about stop words. Well, you didn't mention stop words, but it's the idea of getting rid of some of the terms. Because if you have terms like that, and you're indexing the web, then you will have so many documents that your postings list is going to be huge. So maybe you want to get rid of them. This is called the stop word. You just ignore them. If it's in a query, you ignore them. If it's in a document, you ignore them. There is this list, which is kind of a standard. It's the Reuters list, which I think there's 25 of them in there. It's a standard list of stop words that you can reuse. So this is typically easy to implement. All you need to do is remove it everywhere. However, I have to tell you, even though it used to be very popular in information retrieval to have stop words, we are going from a trend in the ancient times of computer systems where we had a very large list of stop words just because of the limitations of our infrastructure. We couldn't afford to deal with them. And the more time elapses and elapses and elapses and elapses, the less stop words, up to the 25 of Reuters, and now no stop words at all. If you query under Google, you can even use stop words like V, and like V could mean times higher education if you're looking for a ranking. So I think that Google doesn't even use stop words at all. So just to tell you that you need to know what that is and know that the trend is going towards having less and less stop words, if maybe even none at all. Why? Just because we can. We can afford to have the posting lists also for the stop words. So now the types, something more about the types, what I mean with types. So remember, a token is an occurrence of a term in the documents, and the terms themselves can be grouped into meaningful equivalence classes. Who knows what an equivalence class is? Yes? Can you tell me mathematically? Who can tell me mathematically the three properties? So it's a relation that I'm telling you. Three properties of that relation. Anybody? Transitive? Yes? And symmetric, exactly. So here we have exactly this, a relation that is reflexive, transitive, and symmetric. What that means concretely is that you can partition the set of terms into bags. So, not bags, I shouldn't use the word bag in that way, into partitions. So you can say that U.S.A is the same thing as USA, window, Windows, and Windows with uppercase, the operating systems. Today, yes, if you index text from the 19th century, you will find dashes in the middle of today, 2-day, 2-morrow. As I told you, a few decades later, we got rid of it. This is why we no longer have it today. But we need to be aware that it used to be the case. So we also need to take care of that. And of course, if you ask how to write Zurich, then you have the English version, the German version, the version without the umlaut, the Zurich version, and so on and so on. But every time you're looking for the same thing. Even though, again, just like for Windows, you may also mean the insurance company. So you always need to keep in mind that there may be some ambiguity. But anyway, what we want to do here is group the terms into similar packets in order to treat them the same. And what we will do is then when they are in these packets, we can have a single posting list for them all. We pick one of them as the head of the posting list, and all of the occurrences will go to the same posting list, okay? This is one way of dealing with these differences in order to keep the size of the index under control. Who understands equivalence classes of terms? Oh, not a lot of hands. Who doesn't? Okay, I'm assuming you're just shy. So the idea is that you can, when you have these equivalence classes, you can pick in each class one term that is basically your best choice. And every time you say you see this, you replace it that way. Every time you see this, you replace it that way. You can have this with rules as well that remove characters, like you can remove the dot, you can remove the dash, and so on and so on. But I hope I showed you before the break that this was very tricky. There is another idea, which is not the same as equivalence classes. So equivalence classes is one way of doing that. There is another way, which is not symmetric. Equivalence classes are fully symmetric, but here we are not symmetric. It's the idea of expansion. Whenever you see Windows, you keep it as Windows. If you see it lowercase, then you expand it to Windows, Windows, Window. If you see it Window, you expand it to Window and Windows, right? So this is an idea. It's not fully symmetric because you see that you expand Window to Windows and Windows to Windows, but not the other way around. Like here you have an arc here to here, but you don't have going back from here to here. So it's not symmetric. It is also not transitive and so on. But this is called query expansion. It's a different way of doing that. Why does it make sense? Because maybe if somebody just wrote window without an S, then you don't want this to be interpreted as an operating system. right? So this is one of the reasons to break the symmetry. And if you do expansion, what you do is basically, there's two ways of doing that. Imagine that we have a query here, and we have an index that we've already prepared, the documents. And we want to kind of say, if you query for lift, then you should also find the elevators. Okay? As it is now, we won't. If you look for lift, this is the first version of the index. It only returns 1 and 5, but it will not return 4 and 6. So how can we get this to work? There's two solutions. The first one is to expand the index, meaning that if we know that we want to expand lift to elevator, then we add everything here into here. So we have 1, 4, 5, 6. And if we do it symmetrically, using equivalence classes, we don't have to, but we can, then elevator will also be expanded to lift. So here it's symmetric. Just don't assume it's always. And then when you look up lift, you use the expanded index, and you return all the documents. And that means you will also see documents with the word elevator. Okay? The other way of doing that is just the opposite way. Instead of expanding the index, you expand the query. Meaning that if you query for lift, then automatically you rewrite the query internally as lift or elevator, and then you take these two lists and compute there. Just checking you're following. There? Yes? Union, exactly. The problem of easy questions is that I'm sure that a lot of you knew the answer but don't dare answering, but don't hesitate to do so. I have a question, by the way, on query expansion. I told you there's two solutions. Either you expand the index or you expand the query. But what does it look like in terms of space and time compromises? There may be several answers in there. (22). I'm waiting for 3 and 4. Yes. Exactly. So the idea is that index expansion needs space because you're actually storing the index. Even if it's just in memory, it takes space. And of course, the query is going to be slower if you expand the query because you need to compute the union. If you expand the index, the union is already pre-computed. That's why. Oh, by the way, if you're interviewing with a tech company and you have interview questions and they make you solve an algorithm and you have the feeling it's as fast as it gets and they tell you how can you make it faster, the answer is pre-compute, pre-process. This is exactly what index expansion is doing here. We are pre-processing the union at the cost of some space. Okay, so when to expand? So then there's plenty of other things. So here I'm just quickly going over it. You can remove accents. It's called diacritics for the linguists. Cliché, cliché. You can replace the umlauts with the additional E and so on and so on. You can lowercase everything, even though it may not always be a good idea. But that's also something that is typically done, lowercasing everything. There is also the idea of true casing, meaning that you want to distinguish between an apple that you eat and the brand Apple computers. And this is, again, machine learning. Machine learning can classify the words depending on what is actually meant here. So we are not covering, except that you can use machine learning in order to learn and do that automatically. Stemming is yet another way of doing it, of computing these equivalence classes. The idea is that every word, you remove some useless letters, like analysis becomes analysis, feature becomes feature, easily. So it's just a kind of a chopping of the back of the word. And that way, when you have window and windows, then the S is chopped out, okay? There are algorithms to do that. The most famous one, and you must know that it exists, is the Porter stemmer. It's just a bunch of rules like this to rewrite, and you just need to apply them. There are several stages of this, and you just use the rules and follow them. It's fully automated. Go to that page if you want to learn more about the Porter stemmer. It's basically going to do the chopping automatically. there's plenty of other stemmers. There's the Lovins stemmer, there's the Pi stemmer. They are all doing the same thing more or less, but they may differ. You can see that they don't chop in the same way, but they all do a pretty good job. And if you have to pick one, then the Porter stemmer is really definitely the popular one. So you can see what it does to text, right? And this, what we have here, what is this called? Each one of these things here is called a... Who thinks it's called a token? Who thinks it's called a term? Who thinks it's called a type? Who thinks it's called a type? Who thinks it's called a type? Yes, these are types. Because again, what we are doing here is we are building equivalence classes. We are chopping, and what we get after the chopping is the equivalence class. This is a type. Okay? And then in the postings list, in the inverted index, this is what you are actually going to use. And this takes care of the equivalence classes. Who understands this? Okay. And the other way, so the chopping, so the stemming is one way. The other way is smarter. It's actually using an understanding of the language. This is the natural language processing. If you actually know the grammar of the language, then you know that Windows is a plural form of window, cat is a plural form of cat, doing is some alternate form of do, a conjugated form of do, and so on and so on. This is also out of scope, but you should know that some people do that, and then you can basically establish this is called the Vauquois triangle in natural language processing. If you abstract away from a text, you get the syntactic structure, then at some point the semantic structure, and this is the absolute holy grail of when you process languages, is to have this language independence level of understanding, right? So if the computer actually understands the text, then it's even better to do the classification and prepare the types as equivalence classes, because you know that you're doing it semantically correctly, okay? Again, this is going in the direction of artificial intelligence, because we really would have a computer that is capable of understanding the language. So refer to Introduction to Machine Learning, Natural Language Processing lectures. So typically, this is what happens. When you are capable of doing that, you can know that all these words are related. Computing, computation, computed, computes, compute, and computer, and so on and so on. So then comes the question. There's two solutions. Either you use the Porter stemmer, for example, or you use NLP in order to do it more intelligently. It turns out that lemmatization often doesn't help. So you don't need to throw in artificial intelligence and so on and so on. Just use the Porter stemmer, will do quite a good job. And sometimes lemmatization with NLP can even make it worse. For English, again, it depends on the language. For German, maybe it's a better idea. For German, you may want to use these kind of tools because you want to, all the cases, you know, dative, genitive, and so on. You may want to actually have the computer understand them rather than just chopping them with the Porter stemmer. So yes, this is what is being said here. And I think Spanish is also quoted. I don't know Spanish, but I think it's also cited as one of the languages where lemmatization can help. Lemmatization is the stemming. It's when you no, sorry, I got it wrong. Stemming is good for English. Lemmatization with NLP is good for German and Spanish. There, yeah. Did I confuse you because of that? It's very clear, right? Stemming is just the chopping, language independence. The Porter stemmer is good for English, and lemmatization is you actually understand with NLP. Okay, so now we are done with the part about figuring out the documents, the tokenization, and so on and so on. So it was worth spending some time on it. So now we have the documents, we have prepared them, we have tokenized, we have maybe stemmed, and so on and so on. And we have our inverted index. Let's call it the standard inverted index. Now, I would like to make it even better. I would like to make it even faster. So let me give you an example. We have this index, a standard inverted index. It has a few terms. It even has a few types, if you did the work with the equivalence classes and the stemmings. And it has, for each type, the documents that correspond to it. Do you remember what we have in purple here, the first numbers, what this is? Document frequency, right? Every time we have the count of the documents in there. Okay, so now we had the intersection algorithm that allows loaders to compute the intersection of two postings lists. But here is another example where we compute the intersection of two lists. So 1 is the same, so okay, we advance by 1. This is not the same, we advance. 3 is the same, we copy it over. 4, it's different, we advance. 5 is different, we advance. 6 is different, we go forward. 7 is different, we go forward. 8 is different, we go forward. 9 is different, we go forward. 10 is the same, we copy it over. 11 is different, 12 and 12 are different, and there we go. By the way, this is not even needed because we already finished the first one. Okay. This was boring, and it was even more so boring because it was very inefficient. Because what happened here? Yes?
We trade through a very long list because the value almost quite short. So.
Yes, we had a very long list of postings that were not in the other one, so the whole time we were going forward. So how do you fix this? Yes.
Entries. Probably either we can do something static, or we can do like estimating, like first I go 1, then I go 2, 4, and like I get more confident if then I have to go further in order to reach the large event.
Very interesting. So there's two things that you said. The first one is exactly, so I'm going to start with the first one, which is what I expected. I could take something out of a magic hat. And if I could take something out of the magic hat to help, that would be a magic pointer. Because if I had this magical pointer that tells me, here I have this express lane that directly takes me to 10 here, then I can take it and I can ignore all of that. Because I know that this is an ordered list of document IDs. So if I have this magical pointer, it works. There's also something interesting. It's not actually, it's very good to think like that out of the box. You could try saying if you notice at some point that you really repeatedly have misses, then you just try skipping 1 and then 4 and then 8 and then 16 and repeating in the microphone. And yes, that is very clever. Then you could also dynamically try doing something like this. And if you see you're gone too far, then you just track back and trace back and so on and so on. That's a very good idea. It's not actually in the material and so on, but I really must say this is a good idea. Yeah. So we have this magical pointer, and then you can directly jump. When you're here, you jump, and this is, you can see that it was computed more practically. So this is how it could look like in practice. For example, maybe we won't directly jump to 10, which is the magical thing. Maybe in Harry Potter you have these kind of pointers that give you directly the solution, but in practice you would have more like these skip pointers like this, and every time you can choose to use it or not. Maybe you don't want to use it because you see that you want to see 2 and 3. Maybe you use this one here, and then you go like this. Okay? So this is how it works. But be careful, because if you have 2 short skips, that can happen if you have too many pointers everywhere because you want to use them, then that's a very good thing because you are actually going to use them a lot. The problem is that you compare a lot and you don't really gain a lot of efficiency by doing that. Plus you are wasting space because you need to store these skip pointers. So this is one of the extremes to avoid. The other extreme is to really have this huge spring. You're jumping over a lot of postings. The problem is that in practice, maybe you're never ever going to use this one because you are always going to have a few here that you actually need. So this is the other extreme. It's very good because you have few comparisons. On the day that you actually notice that you can use it, then you are going to be extremely efficient, but this is going to be rare. So not many real opportunities. So how do we do it? What do you think? How do we set, ideally, or what is typically advised as a skip pointer size? By how much should we build statically these skip pointers? Okay, let me close. Oh, yes, 23. Yes, oh, 28, wow, okay. Yes, absolutely. Who answers this without looking at the slides? Wow, very good, okay. So indeed, the square root of the length. So the idea is to do this. If you have, here we have 16, a document frequency of 16, so 16 postings in that list. So typically, we take the square root, which is 4, and we have as many pointers as their length, basically 4 times 4, which is the ideal advisable case. I'm not saying it's in all cases. You can always find some use cases where another number is better. But in practice, this is what it's done. You take the square root. Okay? For every, it may be different between the terms, right? Every term may have a different number of documents. Okay, so who understands the skip pointers? Very good. So now let's jump to another thing. This is a feature. This is a new feature. I told you last time that we had this query language with and, or, nor, and so on. What it does not do is phrase search. If you search for example, ETH Zurich, you will see that Google is actually smart enough to really return ETH Zurich. But it could have returned a page on some insurance company that discovered the blockchain and decided to buy some Ethereum currency, right? It could have found that. But somehow it didn't, because it did assume that you wanted to find two words that are very close to each other or even following each other in the page. So you see that Google is not just saying ETH and Zurich, but it's really trying to do something that is called a phrase search. So typically the way that to do it explicitly, because Google does not always do a phrase search. It sometimes does, it sometimes doesn't. It tries to figure it out. If you want to force a phrase search, the way you do that is by adding quotes. If you add quotes, you're telling the engine that you want to do a phrase search. So can you do that with this? If I give you the posting list, can you answer the question, the phrase search ETH Zurich? Who can? Who knows that they cannot? Okay. Yes, indeed you cannot, because we have no idea. We may have documents that contain, like for example, document 1 may contain ETH and Zurich, but it could be about Zurich insurance and the Ethereum blockchain, right? So you don't know. So there's two approaches that I'm going to introduce to you. The first one is byword indices, or phrase indices in general, and positional indices is the other one. You may also hear, I'm going to say the word I cannot resist, bigrams, trigrams, and so on. I should not tell you that because normally we only use that next week for when we actually talk about characters. But just know that it's very similar. So here I'm going to be very careful. I cannot guarantee I won't do the mistake. I will try to be very careful calling it a byword index or a phrase index. Okay, so let's start with the byword index. The byword index. So basically, we are going to index this document. But instead of building an entry in the index for every word, we are going to build an entry in the index for every Tell me, how do you do phrase search? What do you use in the index? Anybody? Okay, who knows how to do that, but just didn't raise the hand? Okay, then let me directly tell you. So in the original standard inverted index, we would have help as a term, and then ETH, and then Zurich, and then to, and then flexibly, and so on. So we take each term, and then we have the vocabulary, and we have the posting list. But what we change here is by word, 2 words. We take the words 2 by 2. Help ETH, 2 words. So we create an entry for all the documents that contain help ETH. Really, one after the other as a string. Then we say ETH Zurich, and we have all the documents that contain ETH Zurich, and then Zurich 2, and then 2 flexibly, and then flexibly React, and then React 2, and so on and so on. We try all the combinations of 2 words that are following, okay? So how do I answer now the query ETH Zurich? The phrase query ETH Zurich. Anybody? Okay, this time I think I know you know. So I'm just going to tell you. You simply look up the two words that you want in the byword index. So you see ETH Zurich here, and you are simply going to return the documents that are in here. And there you go, right? So this is the trick. You change what you index here. You no longer take single words, but you really take pairs of words that follow each other, and you build the index differently. And here you have the guarantee that the documents in there actually contain ETH Zurich. Okay? So if you query, this is what you get. Okay? Who understands this? Okay, so now I know that you knew how to do it. So how do I now treat this one? I basically, again, convert it to a phrase, to some Boolean query, but I'm trying to here take exactly the way I did it with the original document, help ETH, ETH Zurich, ETH2, to flexibly react. So now I have these bywords here, these pairs of words, and this now I can look up here. So I can find this, and then I compute, I take the posting list, and I compute there. You should say everybody at the same time there. Yes, I'm hearing it, intersection. The intersection because it's an and here. And if you take the intersection of all of this, then you will return all the documents that contain this. Nobody has a problem with that? So yes, we will have perfect recall. Remember, the recall is any document that matches, we will return it. But could we have too many documents? And the answer is yes, we could have too many documents. Because imagine this document here. It shouldn't be returned. It's not an actual match. It doesn't contain help ETH Zurich to flexibly react as a phrase search. However, look at the bywords. Check, 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 check. We have them all. So it will be returned, and that's called the false positive. So it means that we won't have perfect precision. We lose in precision. Okay? So how do we improve the precision? Increasing the precision, again, if you remember, means decreasing the number of false positives. If you don't have any false positives, then you have a perfect precision. If you don't have any false negatives, you have perfect recall. And by the way, precision and recall is also something that is used in machine learning. So I'm sure that you also saw that in Andreas Krause's lecture, precision and recall. $23, $25. Okay, let me close. Last chance. Okay. Yes, you make the tuples bigger. This is called phrase index. So the first one is just bringing phrase search, but as we saw with the problem of false positives, post-filtering actually works. Post-filtering works, but this is wrong. There may not be any false negatives because we don't have any false negatives. We have perfect recall here. So this is, we could use post-filtering, but not with this drawback. And phrase indices with smaller tuples of words, well, it would make things worse because smaller than 2, that's basically 1. And if you say ETH Zurich with 1 word indices, that's basically the standard inverted index. And then you don't know anything about the proximity of ETH and Zurich. So if you reduce the size of the tuples of words smaller than 2, you actually have even more false positives. You have even less precision. Okay, so this is the correct answer. One more thing is that you can also, it's a bit similar to stop words, but basically you can tag the part of speech. This is also natural language processing. It's done in the NLP lecture. If you can actually tag text like this with N that says that's an important word and X means it's like a preposition or something or a stop word, then you can actually change what you index. Like here you can say, you can have Zurich introduce, but you skipped 2. You can have techniques flexibly and so on. That's one of the tricks to improve the index and maybe make it slightly smaller. And now getting back to the question that I asked you, we have a lot of false positives, low precision. We can make it 3-word indices. And here you can see that it probably goes away. The false positive now should go away. We can make it even 4 words. And then the false positive issue is gone, because now this is a true negative. A true negative because it shouldn't be returned, and we no longer return it. So we don't have the precision issue. Okay, so we solved the precision issue. We made the tuples bigger. Let's say we have 4 word indices. What problem do we have now? What did we trade better precision for? Yes? Storage space, exactly. Try to implement that. Well, maybe you should with 2. I think it's even in the exercises, you should program that. But try to do it with 3 and 4, and you will have big problems. Because the problem is that if you consider already the size of a vocabulary, let's say in English 70,000, that's a lot. But now, a byword index, that's the square of that, potentially, because I'm not saying there will be any single occurrence of every pair, but potentially it's the square. 3 words, it's cubic. 4 words, it's quadratic. So basically, it's exponential if you vary the number of words in the tuples, which is the exponents. So we have a big problem is that, yes, we have better precision. Yes, we have a correct implementation of a phrase search. We can get rid of any false positives that may have been missed with post-processing, but we have an exponential explosion. So we need other ways to deal with that. And this is where the other technique, so not the byword indices, but the positional index actually kicks in, and it can be very helpful. It's the idea that we modify the index, but in a different way. So let's come back to the standard index. We still index the words one by one. But what we will add here, instead of just having the document ID, which is in that case C, we will also add the position of that term in the document. So here help is at position 1. So I'm saying 1. When I index, so this is the document ID. Oh yes, I'm also storing the number of occurrences. So you see, before that, in our first approximation, we lost that information, the number of occurrences with the order. Here, we actually get it back. We extend the index to keep track of the number of occurrences. So we add back the information. This is no longer the standard index, the standard inverted index. This is a positional index. So we have the term frequency, and we have the positions. So ETH now is at position 2, also a frequency of 1. Zurich is at position 3. We have 2 that is at 3 position, 4, 7, and 11. So it's a term frequency of 3. Oh, note that you would also have the document frequency in here. So we have both the term frequency in every posting and the document frequency for every term or type. Note that if this is a stop word, we would just throw it away, right? But let's say we don't have any stop words. FlexiB is at position 5, React is at position 6, and so on and so on. So now, how do we answer this query? Can we answer this query? So that's not a byword index, right? It's a positional index. How do I do that? Anybody can tell me? Yes?
Well, we look for every single verb, and then sort filter like for documents that have consecutive positioning for those.
Yes. So we query, I'm repeating what you said, we query for the words ETH and Zurich. So now we have documents that contain ETH or Zurich, but we have the positions in there, and we can compare them. And we can see here that Zurich is in this document, it's the same document C, is at position 3 and ETH at position 2. So we know for sure that it's an occurrence of the phrase ETH Zurich, right? So this is actually it. You did well. So here are the next steps. As I said, every week we have an exercise session on the week before, meaning that today's exercise session is going to be about implementing the standard inverted index that we saw last week. So nothing of what we saw today. And everything we saw today, the tokenization and so on, it's all taken care of. The parser is all taken care of. You don't need to worry about the context-free grammar and everything. You will just have everything focused on implementing the standard inverted index. You will have also to implement the intersection, union, optimize the end knot, and so on and so on. The way we are trying to do that, I call it exercise sandboxing. It's the idea that we don't have this big project or a big project in the lecture where you build a full system, but we are going to try to have you build the parts of the system every week, implement what we saw, because it validates that you correctly understood. We will build in some weeks on top of what we did before, but every time, don't worry, we will give you again the source code, meaning that this week you will build the standard inverted index. The week after that, we will build something based on that, but then we will give you the codes, so you won't have to worry about reusing the code of the previous week and so on and so on. So every week you will only have to focus about really the topic of the week, and everything else is taken care of by the TAs, right? Okay, so if you have any questions, then we are here. Apart from that, I hope that you have a good exercise session. Please do try to implement to do the exercises and implements. It's a good preparation for the exam. What did I want to say as well? Yes, don't forget that we will take 3 weeks in which we will actually look at what you did, and you will get extra points for the exam if you actually did 2 of these 3. So you are really encouraged. It's good for you to do this, and the extra points are just a bonus to make it even more interesting. So thank you very much, and then enjoy your meal and your weekends after the exercise session.